2 minutes ago, if you looked at the deepest image ever taken of the early universe, you would have seen something scattered across it that nobody could explain. Not galaxies, not stars, not black holes, not exactly. Small, compact, blazing red points of light, thousands of them, sitting in the part of the universe that formed less than 1 billion years after the Big Bang. Astronomers gave them the most understated name in the history of astrophysics. They called them little red dots. And for almost 4 years, nobody could tell you what they actually were. Most people who follow space news know the big headlines out of the James Webb Space Telescope. The deepest galaxy ever found, the most distant black hole ever measured, the stunning image of the pillars of creation in infrared. Those stories get the views, the front pages, the viral posts. But buried inside Webb's early data, almost from the very first month of science operations, was a puzzle that quietly became one of the strangest unsolved mysteries in modern astronomy. And it did not look like much, just a red dot. Small, faint, easy to miss if you were not looking for it. Except the universe kept handing astronomers more of them, hundreds, then close to 1,000, all from the same narrow slice of cosmic history, all sharing the same strange, almost impossible characteristics. And what researchers now believe is hiding inside them is stranger than almost anything else Webb has found. Stick with me, because this is the story that most space channels still have not properly explained. And by the end of this video, you will understand something that a huge share of the people currently talking about James Webb do not. Subscribe now, because there is more breaking down every single week, and this particular mystery is still not finished unfolding. Let's start with when this actually began, because the origin of the little red dots is almost as strange as the objects themselves. The James Webb Space Telescope, launched on Christmas morning in 2021, unfolded itself over the following month in a sequence of more than 300 single points of failure, and reached its final orbit nearly 1 million miles from Earth at a gravitationally stable point called L2. By the summer of 2022, its instruments were calibrated and its first science images were released to the public. Everyone remembers those first images. The glittering deep field packed with thousands of galaxies, the cosmic cliffs of the Carina Nebula. What almost nobody remembers is that buried inside those very same early datasets, astronomers doing spectroscopy on faint, distant sources kept running into objects that did not fit any known category. They were compact, almost point-like, the way a star or a very distant unresolved galaxy might look. They were intensely red, far redder than ordinary dust could explain, and they were, sitting at redshifts that placed them just a few 100 million years after the universe itself began. In plain terms, Webb was looking back roughly 13 billion years into an era so early that galaxies as we know them should barely have had time to form at all, and yet here were hundreds of small, blazing red objects packed into that impossibly young slice of cosmic history, defying easy explanation. Astronomers needed a name for them fast because papers were piling up and nobody had a formal classification. So they called them exactly what they looked like on the screen: little red dots. Here's the detail that made this genuinely strange, and the reason so many astronomers got hooked on solving it. Objects at that distance from that early era of the universe are supposed to be faint, extremely faint. Light takes billions of years to reach us, and it stretches and dims across that journey. So when researchers see something bright enough to detect clearly at that redshift, the honest assumption should be that whatever is producing the light must be enormous, a massive galaxy packed with billions of stars all shining together. Except the little red dots were far too small and far too compact for that explanation to hold up cleanly. Something inside them was producing an enormous amount of light from what appeared to be an astonishingly small physical space. And that combination, huge luminosity, tiny size, deep cosmic distance, is exactly the signature that points toward one very specific kind of object in astrophysics, a black hole that is actively feeding. That was the first serious theory, and it is where the first major surprise in this story comes from. If the light really was coming from a supermassive black hole pulling in surrounding gas and dust, then the mass required to produce that much light using standard physics was almost impossible to reconcile with how early these objects appeared in cosmic history. Supermassive black holes are supposed to take time to grow. They start from a seed, whether that seed is the remnant of a collapsed massive star or something more exotic, and then they slowly accumulate mass over hundreds of millions or billions of years as they pull in surrounding material. But some of the little red dots appeared to require black holes already carrying tens of millions. In some extreme cases, over 100 million times the mass of our sun, at a point in cosmic history when the universe itself was barely 600 million years old. That is not enough time, according to the standard growth models, for a black hole to reach that size through ordinary accretion. For a while, some astronomers half-joked that the little red dots had broken cosmology itself, because the numbers simply did not add up using the physics everybody trusted. Then in January of 2026, a study published in the journal Nature, led by researcher Ivan Rusakov and his colleagues, delivered the first piece of the solution. And it was not the piece anyone expected. The problem was not that black holes were growing impossibly fast. The problem was that scientists had been measuring their mass wrong from the very beginning. The team found that the black holes powering little red dots are likely around 100 times less massive than earlier estimates had suggested. The reason came down to the dense cocoon of gas surrounding each black hole. That gas was artificially broadening the spectral lines astronomers use to estimate mass, mimicking the signature of an object far heavier than what was actually there. In other words, the black holes were not impossible monsters that broke the rules of cosmic growth. They only looked that way because a thick shroud of gas was distorting the measurement, like trying to weigh someone while they are wearing 15 winter coats and assuming all that bulk is muscle. Once that gas cocoon was properly accounted for, the black hole masses dropped back down into a range that standard growth models could actually explain. The mystery did not vanish, but the numbers stopped screaming for a complete rewrite of physics, and researchers could finally start asking a better question. If it really is a black hole wrapped in gas, what does that actually look like, and how do you prove it? That question leads directly into the second major discovery, and this one came from the deepest, most detailed look any single little red dot has ever received. In June of 2026, a team of astronomers led by Vasily Kokorev at the University of Texas at Austin published results built around a specific object cataloged as Glimpse 1.5, found sitting behind a massive galaxy cluster called Abell S1063. That cluster happened to work as a natural magnifying glass through an effect called gravitational lensing, bending and amplifying the light of anything positioned directly behind it. Webb had already spent 30 hours gathering a spectrum of this object as part of an entirely different research program, one originally designed to hunt for a theorized population of ancient stars. But because of the lensing boost, that 30 hours of observing time behaved more like 80 hours worth of signal. The result was the most detailed spectrum ever captured of a little red dot, containing more than 40 distinct spectral lines, each one acting like a fingerprint revealing something about the physical conditions inside the object. What that spectrum showed stunned the team. The hydrogen, oxygen, and helium lines did not match what you would expect from a simple rotating disk of gas around a black hole. Instead, the light showed the signature of something called electron scattering, a specific kind of distortion that only happens when light has to fight its way out through an extremely dense, layered cocoon of partially ionized gas. On top of that, the spectrum contained 16 separate iron lines, so densely packed together that the research team started calling it the iron forest, along with oxygen line ratios that could only be produced by an extremely energetic source at the center. The combination pointed toward one specific explanation: a rapidly growing black hole wrapped inside a hot, dense shell of gas that is absorbing the harsh radiation coming off the black hole and re-emitting it as the strange red glow that gives these objects their name and their color. Researchers have started calling this scenario the black hole star, sometimes shortened to BH star. Not a star in the traditional sense of nuclear fusion happening in a core, but something that behaves almost like one from the outside. A compact glowing object, powered from within, wrapped in a shell so thick that almost none of the black hole's most violent radiation escapes directly. Instead, it gets absorbed, reprocessed, and released again as the deep red light that Webb keeps finding scattered across the early universe. This also solved a smaller but genuinely puzzling side mystery. If these objects really contained actively feeding black holes, astronomers expected to see them shining brightly in X-rays, the way growing black holes usually do elsewhere in the universe. But most little red dots stayed stubbornly quiet in X-ray surveys, which had confused researchers for years, and led some to doubt the black hole explanation entirely. The black hole star model explained that too. The same dense gas cocoon responsible for the object's red color was also thick enough to absorb almost all of the X-ray emission before it could ever escape into space. The silence. In X-rays was not evidence against a hidden black hole. It was actually more evidence that one was buried underneath all that gas. But even with that piece in place, one more question remained open, and it led to the third major discovery in this story. If little red dots really were black holes wrapped in gas cocoons, there should logically be some objects caught in between stages. Some that are just beginning to clear away enough of their surrounding gas to start leaking X-rays out into space, acting as a bridge between the deeply hidden black hole stars and the more familiar, fully exposed supermassive black holes astronomers have studied. For decades in the more recent universe, that bridge object turned up almost by accident. Researchers using NASA's Chandra X-ray Observatory noticed a faint X-ray source sitting in a patch of sky that Webb had already surveyed for little red dots. And when they lined the two data sets up, that faint X-ray source matched the exact position of one of them, an object now cataloged as 3DHST Aegis 2014 and nicknamed the X-ray dot, located roughly 11.8 billion light years from Earth. What made this discovery remarkable is that this particular little red dot had actually been sitting quietly inside Chandra's archived data for more than a decade, before anyone realized what it was looking at. Nobody had connected it to anything unusual because, on its own, faint X-ray sources are common. It was only once Webb identified it as a little red dot that the older Chandra data suddenly became significant. Astronomer Andy Goulding at Princeton, one of the researchers involved, pointed out just how strange it was that this signal had been sitting in the archive for over 10 years without anyone recognizing its importance, until Webb gave them a reason to look again. The X-ray dot appears to represent exactly the transition phase researchers had been looking for, a little red dot that has started to clear enough of its dense gas cocoon to let some high-energy radiation leak through, caught in the act of evolving from a hidden black hole star into something closer to the more exposed, actively feeding supermassive black holes seen later in cosmic history. If that interpretation holds up, it means little red dots are not simply a strange, isolated category of object. They may represent an entire missing evolutionary stage, the link between how the very first seeds of supermassive black holes formed in the extreme conditions of the early universe and how those same black holes eventually became the enormous, well-studied engines sitting at the centers of galaxies like our own, billions of years later. Now here's where the story gets even stranger, because solving the black hole star question did not close the case on little red dots. It opened up an entirely new one. Astronomers noticed something odd once they started tracking how many little red dots appeared at different points in cosmic history. Their numbers rise steadily the further back you look, all the way to around 600 to 800 million years after the Big Bang. Then, at a certain point in cosmic time, roughly corresponding to about 12 billion years ago, the population of little red dots drops off a cliff. Almost none are found after that point. They do not fade out gradually, they essentially vanish. And for a long time, nobody could explain where they went. That question finally got a serious answer in July of 2026, when a team led by researcher Ivo Rinaldi published new results built around an object nicknamed the saguaro, formerly cataloged as Wissia J63556 plus 62424.2. The explanation turned out to combine both earlier pieces of the puzzle. First, remember that the black holes inside little red dots had already been shown to be smaller than originally believed, once the gas cocoon's distorting effect on their measured mass was corrected for. Second, and this was the new piece, the host galaxies surrounding these black holes were never actually missing. They were simply too faint and too spread out for Webb to detect against the glare of the object's own light at that extreme distance. Only the compact blazing core, the black hole star itself, was bright enough to survive the 13 billion light-year journey to Webb's mirrors in a form that could be clearly picked out. As the universe aged and these objects evolved, their surrounding host galaxies would have started to grow larger, and their black hole star cores would have started to fade or become obscured differently, changing the ratio between the two. That shift in balance is likely why the little red dot signature disappears from the data after a certain point in cosmic history. They did not die out. They evolved into a form that no longer produces the exact same telltale red glow, blending into the broader population of ordinary, growing, supermassive black holes that astronomers have been studying in less extreme, more familiar galaxies for years. Put all three discoveries together, and you get a genuinely coherent story built entirely from real, published, peer-reviewed research across the last 8 months. Little red dots are almost certainly the earliest visible stage of supermassive black hole growth in the universe, caught in a violent, short-lived phase where a rapidly feeding black hole is still wrapped inside the dense cocoon of gas it has not yet cleared away. As that gas thins out over time, some of them briefly leak X-rays, caught mid-transition, like the X-ray dot found hiding in old Chandra data. And eventually, as their host galaxies grow larger around them and their own internal structure shifts, they stop looking like anything Webb classifies as a little red dot at all, fading into the general population of black holes that quietly sit at the centers of galaxies throughout the rest of cosmic history, including, most likely, the supermassive black hole sitting at the center of our own Milky Way. Take a moment to actually picture what one of these objects would have looked like up close, because the scale involved is almost impossible to hold in your head properly. Picture a region of space smaller than a solar system, sitting inside a galaxy so young that its stars have barely had time to form and explode even once. At the center of that region is a black hole, already carrying the mass of tens of thousands, sometimes millions of suns, tearing apart infalling gas and compressing it to temperatures of millions of degrees. That radiation should be blinding, catastrophic, the kind of light that would scour clean any nearby gas within a short cosmic time frame. Except here, it isn't escaping cleanly at all. It slams directly into a dense, churning shell of surrounding gas, itself hundreds of times denser than anything found around black holes in the more recent universe. That shell absorbs almost everything, glows white hot on the inside, and slowly re-radiates that trapped energy back outward as a deep, smoldering red, stretched even further toward the red end of the spectrum by the expansion of the universe itself during the 13 billion years that light needed to finally reach a mirror built by human beings on the far side of the cosmos. From any reasonable distance, an object producing that much raw energy should look enormous. Instead, from 13 billion light years away, it shows up as nothing, more than a single stubborn, blazing point. A dot, small enough to almost dismiss, violent enough to challenge how astronomers thought supermassive black holes were even allowed to form. And here is the part of this story that nobody currently talks about enough. This is not settled science. As of right now, in the second half of 2026, researchers openly admit that competing explanations are still on the table. The black hole star model has become the leading theory, and the evidence supporting it, especially from objects like GLIMPS 1/75 and the X-ray dot, is genuinely strong. But some astronomers, including teams working out of the Center for Astrophysics at Harvard and Smithsonian, have proposed an alternative explanation for at least some little red dots, that they might instead be an exotic, extremely short-lived class of supermassive stars, potentially reaching close to 1,000,000 times the mass of our Sun, with outer layers so extended and diffuse that their surface temperature drops low enough to produce that same distinctive red color, entirely without a black hole involved at all. Researcher. Alexander G. Frisenga-Braun and colleagues have pointed out that the physical properties predicted for these hypothetical supermassive stars line up strikingly well with what has actually been observed. Nobody has fully ruled that possibility out yet. Astronomer Anna de Graaf, who led one of the largest Webb surveys of little red dots to date, has been direct about the fact that not every little red dot behaves the same way, and that one particular object nicknamed the Cliff appears to actively contradict some of the earlier hypotheses, reminding the entire research community that no single model currently explains every single one of these objects perfectly. That's the honest state of the science right now in the summer of 2026. Progress has been enormous. 4 years ago, nobody could tell you what a little red dot even was. Today, researchers have a leading theory backed by detailed spectra, a documented transition object caught mid-evolution, and a credible explanation for why the entire population disappears from the data after a certain point in cosmic history. But the full picture, the complete, locked down, no remaining doubt answer, is still being assembled piece by piece, publication by publication, spectrum by spectrum. Kokorev himself, the astronomer who led the GLIMPS 17/775 study, has said he expects it could still take another year or two before the community reaches a truly final answer on what is powering the central engines inside these things. Here's why this actually matters beyond simple curiosity, and why every astronomer working on this considers it one of the most important open questions Webb has ever raised. Supermassive black holes exist at the center of nearly every large galaxy in the universe, including our own. For decades, one of the deepest unsolved problems in astrophysics has been explaining how those black holes managed to grow so large so early, given how little time the universe had provided them. Little red dots may be the literal missing link, the actual observed evidence of that critical early growth phase, caught directly in the act, rather than inferred indirectly from black holes that have already finished growing billions of years later. If that interpretation holds, then every one of those thousands of little red dots scattered across Webb's deepest images represents a supermassive black hole essentially being born in real time, frozen in a single snapshot by the simple fact that its light has taken 13 billion years to finally reach us. And there is still far more territory left to explore here than most people realize. Webb has found close to 1,000 candidate little red dots so far, and only a tiny handful of them have received anything close to the kind of detailed spectroscopic study that GLIMPS 1/775 or the X-ray dot received. Every additional deep spectrum adds another data point, another piece of the puzzle, another chance to either confirm the black hole star model completely or uncover something that forces the entire picture to shift again, the way it already has twice in the last 12 months alone. On top of that, NASA's upcoming Nancy Grace Roman Space Telescope is expected to scan much wider areas of sky than Webb currently can, and part of its mission will include hunting for rare, more modern little red dots that may still exist much closer to us in cosmic time, even though they cannot survey nearly as deep into the extreme early universe as Webb does. If Roman finds even a handful of little red dots existing outside that narrow, early window, it could completely reshape how astronomers think about where and when this violent black hole growth phase is actually allowed to happen. So the next time somebody shows you a stunning high-resolution image from the James Webb Space Telescope, take a closer look at the smaller, quieter details scattered around the edges of the frame. Somewhere in there might be a single, unassuming red dot. Nothing dramatic to look at. No visible spiral arms. No glowing nebula. No dramatic structure at all. Just a small, stubborn point of light that has been traveling for 13 billion years to reach you, carrying inside it the exact moment. A supermassive black hole first started to grow, wrapped in gas so dense that almost none of its true violence has ever managed to escape. That is what may be hiding inside the universe's strange red dots. Not a mistake in the data, not a glitch. Quite possibly the earliest confirmed baby picture of a supermassive black hole that anyone has ever managed to capture. If this is the kind of space story you want more of, grounded in real published research instead of exaggerated headlines, subscribe to this channel and turn on notifications, because this mystery is still actively unfolding. New spectra are being analyzed right now. New candidate objects are still being confirmed. And the final answer to what is truly powering these little red dots could arrive at any point over the next year or two. When it does, you're going to want to already understand exactly what you're looking at. Thanks for watching, and I will see you in the next one.